Welcome back to Algorithmic Game Theory. Today we'll be discussing a topic in mechanism design for which, at least for most of us, it is clear that it should not involve any money, namely voting. So what could this mean? We might want to design, for example, a presidential election. We have multiple candidates and then we have to determine who will win presidency. And this might mean that each voter will just say who's their preferred candidate, or they may tell us even more. That's up to our particular design. And if you have only two candidates, then there is a very standard format for this, namely, who wins the election? The one who got more votes than the other. Setting now the issue of tie-breaking aside, because this rarely happens that two candidates would get the exact same number of votes. And this is used very widely, and it is also used for a good reason. Why that? Because only a minority of the voters will not be happy with the outcome. The majority of voters will say, okay, this is my preferred outcome, and in this way there is no better outcome than this one. But things get much more tricky when you have three or more candidates. And probably you've seen this also happening in the elections, for example, for a mayor. That then suddenly you think, okay, I could now vote for my favorite candidate, but he or she has really small chances. So I might want to support my second favorite candidate just because, well, he or she is likely to then get at least a plurality of the votes, and this way get more votes than the guy that I really don't want to have. So there is some strategic voting involved. And that's one of the questions we should ask. Are there ways to avoid this, that the voters will behave strategically, will have to behave strategically? And also, before that, we should ask the question, how do we even determine the winner? So even if everybody told us who they prefer most and who's their second favorite candidate and so on, how would we then determine the winner, because there are better and worse rules. But before we start all this, let's first introduce a formal model, because this is again the problem that we are in a setting without money. So there are no monetary units in which we can express, okay, I like this candidate this much. But instead, we'll again define a preference order. So formally, this will look as follows. We will have n agents, capital N again, and we have m candidates, and we call the set of candidates gamma, capital gamma. Each agent has a complete preference list over gamma without ties, and we will now use the following notation. We will write A is preferred over B is preferred over C with a subscript I if agent I prefers A in gamma over B in gamma and B over C. This of course implies that I also prefers A over C, so we'll have transitivity. And what are now our problems? There is the voting problem, which is the following. Given all these preference orders, we'll have to determine one winner from gamma, and we'll have the ranking problem, which asks us not to only determine a winner, but a full ranking of all candidates. So again, we're given all these preference orders, and our goal will be to determine a society ranking of all candidates. This means that besides only finding a winner, we'll also have to say who's in second place, who's in third place, and so on. So our goal will be now to design a ranking rule or a voting rule, depending on which problem we're in. These two problems are very similar. The ranking problem, of course, asks us to do more, but generally you should think of them as very, very similar because also the fundamental things are the same. So what makes this difficult? Well, we are now given these preference orders of the individual agents, and somehow we'll have to find a compromise, maybe, however you want to call this, and we don't have any objective function. So this is actually up to our design of what we now think is a good outcome, for example, for this voting problem. One way you could approach this is to say, okay, I'm going to take just a random winner from gamma. Or I take the one who gets the least number of votes. In other words, you take these preference orders and then you say, okay, and there are now multiple versions of this. For example, who's at the worst position in the plurality of these preference orders, or who's the first choice for the least number of agents. All of this, of course, doesn't make real sense, but why? Why isn't this a good voting rule to choose the candidate who the fewest voters actually like? This is something that we'll have to formalize. We've all seen examples of voting and ranking rules, and I'd like to now first discuss these and discuss how they fit into our framework and to what extent they turn out to be good or not so good ranking rules or voting rules. And the first one I'd like to consider is plurality voting. How does this work? In plurality voting, you just have one vote. Each voter has one vote, and they just tell the mechanism which of the candidates they prefer most. And then whoever got the most votes wins the election. This we first have to translate into a voting rule in our sense, because we said, okay, a voting rule takes as input the preference orders. And how could we then design this plurality voting? We would just only care about the most preferred of the candidates in each of the preference orders, and then we would simply count how often is one candidate the most preferred. So what we'll do is, for each candidate, count the number of agents who prefer this candidate most. The candidate with the highest number wins. And if you like, you can also turn this into a ranking rule by now saying, okay, who is ranked second in this counting here, this one then will be second in the society ranking, and so on. Is this good? Well, it does have some advantages, but we've also seen some disadvantages probably. If there are two candidates from more or less the same party, and there's a third candidate who's from a different party, then it might be that the voters actually prefer the party of the first two candidates, but none of them is then getting more votes than the third candidate, although all voters would prefer, or the majority of voters would prefer one of the first two candidates. So, more precisely, we could have the following. We could have that 35% of the voters prefer A over B over C. 25% of the voters prefer B over A over C. And 40% of the voters prefer C over A over B. Now what happens here is that 60% of the voters prefer one of A or B over C, but C wins. And this is exactly the problem that I was alluding to earlier. Here we'll see an example where you would probably in reality vote strategically, and if you were among these 25%, maybe you would decide to also vote for candidate A so that he or she gets above the 40% of candidate C. One alternative is to change this voting system and to introduce a runoff vote. And that's something you often see in practice. You'll see this in mayor elections in Germany or also in the presidential elections in France, that you do all of this, but then among the two highest ranked candidates, the two candidates who got the highest number of votes, among these you'll have a runoff vote, and then whoever gets the majority in that runoff vote then wins. So how does runoff voting fit into our framework? We'll again count the preferences as in plurality voting. And among the two candidates who were ranked highest most often, and what we'll then do is we'll ask, are there more I for which X is preferred over Y, or for which Y is preferred over X? And the candidate who gets the majority wins. Okay, so why do we implement this? Why is this so often seen in practice? It is just because usually there would be two more polarizing alternatives, and often then you'll see then in the runoff vote you'll see these two polarizing alternatives, and then you still have to decide on one of these. But given that we have the complete rankings, we can even go a step further than this and not just do this one runoff vote, but we can do instant runoff votes, and this way eliminate one candidate after the other. So this is called instant runoff vote. And what we'll do is we'll iteratively eliminate the candidate who is ranked highest least often among the remaining candidates. That's also a format that you might have seen before, so at least I know this from casting shows on TV, that what they do is that in each week one of the candidates gets eliminated, namely the candidate who got the smallest number of phone calls, for example. And this seems to be just moving this idea of runoff voting further. And in both cases, you can ask the question, does this now eliminate the problematic strategic behavior that we saw with plurality voting, that you actually wouldn't vote for your preferred candidate? Yes, that can still happen. How so? We might have 30% who prefer A over B over C. We'll have 45% preferring B over C over A, and we'll have another 25% preferring C over A over B. And what makes this now actually a difficult example is that you see here this strange cyclic preferences, that actually somebody prefers A over B over C, and then the next group of people, they prefer actually B over C over A, and then it's C over A over B. So this clearly does not have this party structure that you think, okay, people say they prefer one of A over B compared to C, or something like this. This is not happening here. And indeed, what we'll see here is that who wins? Who gets eliminated first? C will get eliminated first because he gets the smallest number of votes in the first round. And then these here prefer A over B, so we'll have to add these 25 to the 30. And so then candidate A wins. But there is the 45%. What if they all prefer C? That if they all voted for C in the first round, then in the first round, A would get eliminated. And this would make this group of people happier. So there is just some strategic behavior possible. Somehow strategic behavior will turn out to be in the interest of at least these 45%. Of course, all of them would have to agree to do this, and this would only work in a setting of full information. What we see here is that A wins, but if the 45% report that they prefer C over B over A, then C wins, which they prefer. Good. Now, what's an alternative? Is there anything that is better? Is there anything that avoids strategic behavior? Yes, there is an example of a voting rule which avoids strategic behavior. And I guess you've seen that also, but you don't like it. Namely, this is called dictatorship. How does this work? This is really easy. As the society ranking, take the preferences of one fixed agent. Yes, and this we can also use as a voting rule, namely whoever this agent prefers most, this will be the winner of our election. The amazing thing about this is that here strategic behavior won't help you. So if you're not this fixed agent, then it doesn't matter what you're voting because nobody cares. And this fixed agent, well, they can just report whatever they prefer most because this is what's going to happen. But at the same time, we feel, okay, this is maybe not the kind of voting or ranking rule that we like. So let's now talk about properties of voting or ranking rules that we do like. What is it that makes such a voting or a ranking actually fair? Who should win elections? What would we consider an appropriate voting or ranking rule? We'll now introduce a couple of properties and then we'll see whether these are fulfilled or not fulfilled for the examples of the voting rules that we've already seen, and we'll also introduce further voting rules for which we will verify them or not. And these properties are as follows. One thing that we might be asking for is anonymity. What do I mean by that? I mean that the identities of the agents do not matter. Which means nothing but that the outcome on the preference profile for the agents in order 1 through n is the same as what we're getting if we're permuting this profile. Another one is monotonicity. If one agent moves up one of the candidates in his or her private ranking, then the candidate should not move down in the society ranking. Or in particular, if we're speaking only of a voting rule, this also means that if I now say okay, I actually prefer this candidate more than before, everything else remains the same, so this candidate just goes up in my personal ranking, then, so in my personal preference order, then in the society, in the voting outcome, it should not happen that before this candidate was winning the election and now suddenly he or she is losing the election. There's another, or there are two more properties. The first one is the so-called Condorcet winner criterion, which is the following. If there is some A such that for all B there are more I who prefer A over B than B over A, then A is the winner of the election. Let's once again digest this. If there is a candidate A for which the following holds, we now just consider all pairwise votes that we could run for A with any other candidate B. And we call A a Condorcet winner if A wins all of these pairwise votes. And if A always wins these, then we call A Condorcet winner. And the Condorcet winner criterion now says, for such a Condorcet winner, it should be that this Condorcet winner is winning the entire election. So also when we now have all candidates together and not just the pairwise comparisons. Analogously, we can also define a Condorcet loser criterion, which is the same thing but with losing. So if there is some A such that for all B there are more I with B is preferred over A, then A is preferred over B, then A does not win the election. So what is this trying to formalize? If there is somebody that actually nobody likes, in the sense that, which is not quite true, but if this somebody is never preferred in any pairwise comparison by the majority of the people, then this candidate should not win the election. And this can or cannot be fulfilled depending on what voting or ranking rules you apply. And let's now see how our examples perform. Let's come back first to plurality voting. And let's recall the example that we had before, namely that 35% prefer A over B over C, 25% prefer B over A over C, and 40% prefer C over A over B. Is there a Condorcet winner here? Is there a Condorcet loser? Yes, both. Namely, I claim that A is the Condorcet winner. What do we have to now see to verify that A is the Condorcet winner? We'll have to see what happens in the pairwise comparisons. So how does A perform in comparison to B? How many prefer A over B? It's these 35% and these 40% who prefer A over B. And it's these 25% who prefer B over A. So the majority prefers A over B in the pairwise comparison. And how about A versus C? These 60% prefer A over C, whereas these 40% prefer C over A. And this way we see that A is the Condorcet winner. Same thing about C being the Condorcet loser, because C will lose both pairwise comparisons. C will lose the pairwise comparison against A, because these 60% prefer A over C, and only these prefer C over A. And the same you get regarding who prefers C over B or vice versa. So we'll see that A is the Condorcet winner, C is the Condorcet loser, but C wins. So this does not fulfill the Condorcet winner criterion nor the Condorcet loser criterion. Run-off vote and instant run-off vote is a little better because it at least fulfills the Condorcet loser criterion. Why that? Because the Condorcet loser would never survive the final round of the run-off vote, where there's only a pairwise comparison. However, it does not fulfill the Condorcet winner criterion. Let's now have a look at another example, namely the border count and positional voting. Positional voting is a pretty general way of designing a ranking or a voting rule. Namely, what we'll do is we will define A1, A2, and so on up to AM if we have M candidates. And what we'll do now is determine a score for each candidate namely for every I that ranks the candidate at position J, we'll add AJ to the score. And then the society ranking is just the candidates ordered by decreasing score. So one easy example would be setting A1 to 1 and all other A's to 0. This will be exactly plurality voting. But you can also do other things, like for example, have a more refined way of defining these scores. Namely, for example, there's the border count, which says the first one to m, the second one to m minus 1, and so on, up to the last one getting 1. This is called the border count. And to understand this, let's again see what's happened in our example. We'll again have 35% preferring A over B over C, 25% will prefer B over A over C, and 40% will prefer C over A over B. And if we now have 100 voters, then we'll get 35 times 3 points for candidate A from the first group plus 25 times 2 points for candidate A plus 40 times 2 points. So in total, this will be 235 for candidate A. And analogously, we get 185 for candidate B. And we'll get 180 for candidate C. So in this case, we would have A being ranked over B over C, and A would be the winner of our election if we took the one with the highest score in the border count. Where does this way of choosing the numbers come from? It comes from the fact that you could also equivalently say, I now do all possible pairwise comparisons, and I just count how many votes does every candidate get overall. So what we'll do is we'll first do the comparison A versus B. And then we'll do the comparison A versus C. And then we'll do the comparison B versus C. And then the ranking that you're getting this way will be exactly the same. There are many other rules like this. For example, you might have also seen this one. A1 is 12, A2 is 10, A3 is 8, A4 is 7, A5 is 6, A6 is 5, A7 is 4, A8 is 3, A9 is 2, A10 is 1, and all others are 0. This would be the way that the Eurovision Song Contest does it. So I don't see any particular reason why to use this way of assigning the scores. Why is it that the one who gets the most votes gets 12 points and not 20 or whatever you prefer? That's just, I think, to some extent up to personal taste. Now the question, of course, we could ask, and we should ask, is how about Condorcet winners and Condorcet losers? Do Condorcet winners always win? Do Condorcet losers always lose? The answer is depends. Condorcet winners do not necessarily win. So the Condorcet winner criterion is not fulfilled. And this is true for any of these rules. Why is this? We might have something like this. 60% of our agents prefer A over B over C, and 40% prefer B over C over A. Now, who will win the border count? Actually, B wins the border count. But A is the Condorcet winner. So we'll see here that agent A would win, of course, both pairwise comparisons. They would always get 60%. So this makes him or her the Condorcet winner. But he's not the winner of the border count. And maybe that's for a good reason, because do we actually want A to win the election? Because these 40%, they apparently don't really like him. Candidate A seems to be much more polarizing than B. B everybody can live with, but A, some people love him, some people hate him. So this is just not taken into consideration by the Condorcet winner criterion. The Condorcet winner criterion only does these pairwise comparisons, and it does not take into consideration how much people like this or that candidate. It is only about the pairwise comparisons. But how about a voting rule that actually does fulfill the Condorcet winner criterion? How could we build that? This would work as follows. This is just one possible rule to do this. This is the so-called Copeland rule. You will just do all pairwise comparisons. And count how often a candidate wins. And then we say that the Copeland score is the difference of how many pairwise comparisons this candidate wins and how many he or she loses. Then the candidates are ranked by decreasing Copeland score. So if we have m candidates, each of the candidates will go into m-1 pairwise comparisons, and this means that the Copeland score will somewhere be between m-1 and negative m-1. And by design now, this fulfills the Condorcet winner and the Condorcet loser criterion, because a Condorcet winner will have a Copeland score of m-1, whereas a Condorcet loser will have the smallest possible score of negative m-1. And so the Condorcet winner, if there is a Condorcet winner, this Condorcet winner will have the highest possible score, and nobody else will have this high score. And if there is a Condorcet loser, then also this Condorcet loser will have the lowest possible score. Good. So one thing we've seen is that there are different ways to design voting rules, and it is actually not quite easy to answer the question, who should win the elections? As a matter of fact, we didn't even talk about monotonicity and anonymity here, because they were always fulfilled, but that's not quite clear. There have been many examples in the past where elections happening in reality, somehow if people just voted differently, somehow, and by that I mean if they, for example, voted quite the opposite of what they were voting, then somehow their preferred candidate would become better. So those are certainly rules that one should keep in mind, or criteria that one should keep in mind. There are even more criteria when designing a voting rule. And what we see is that there are better and worse voting rules, although you'll have to be careful by what you consider the best voting rule, just because is the Condorcet winner criterion now desirable or isn't it? Depends on what actually you feel is most important. However, there is one more aspect to all this, namely strategizing. And this is something that even I myself probably have done multiple times in an election, not voting for my preferred option, but because I saw that my second preferred option had a higher chance of winning, then I voted for them. Is this avoidable? Are there voting rules that avoid this? This is what we'll discuss next. Do agents want to misreport their preferences so that some candidate wins the election that did not win before when they were reporting the truth, and somehow they prefer that candidate that wins now over the one that wins when they report the truth? In this context of voting and ranking, the property that agents can improve the outcome in their favor by misreporting is called strategic vulnerability. And we've seen that all voting rules we were discussing, at least all the ones for which I mentioned this, those are actually strategically vulnerable. We'll make this formal in just a second. Now, is there a voting rule that avoids all of this? And unfortunately, the answer to this is no. This is quite a bummer, and it's a very famous result in the context of voting, that every reasonable voting rule will have to be strategically vulnerable. In the remainder, I'd like to give you an idea of how one can actually argue this. And also we'll have to discuss the precise statement, because there are, of course, voting rules which are not strategically vulnerable. But those aren't reasonable in our sense. So first of all, let's see how we would define this. And let's only talk about ranking rules. And we say that a ranking rule is strategically vulnerable if there are the following: an agent I, a preference profile for all agents, so we'll have a preference for all agents, and we'll also have an alternative preference report for agent I. And we'll have two candidates, A and B, such that agent I actually prefers A over B. And B now gets ranked higher than A, and A will get ranked higher than B, where this greater sign, this is just the society ranking under the true reports, and the one with a prime would be if I now change agent I's report to the other preference. And what we are looking for, of course, is a ranking rule which is not strategically vulnerable, because that would mean that no agent would misreport strategically, which would make voting much easier than if you always have to keep in mind how does this voting rule perform, or this ranking rule. And what we can do now is we can actually rephrase this property of strategic vulnerability in a different way. Namely, we can say an alternative definition that a ranking rule is independent of irrelevant alternatives or for short IIA, if for any two candidates A and B, given two preference profiles for agents, and these two preference profiles are the same with respect to A and B, in the sense that A in agent I prefers A over B in whenever it does so in the other preference profile as well. So in that sense, looking only at A and B and not at the irrelevant alternatives, then A will be preferred over B if and only if A will be preferred over B in the outcome of that other preference profile. So it takes it some time to digest this, and it's actually hard to write this down formally, but the idea is pretty simple. We'll have two candidates A and B. And now look at the two preference profiles, and with respect to only candidates A and B, they look exactly the same. And then we say, okay, the pairwise ranking of A and B, that should be the same under both preference profiles. So if in this preference profile A is preferred over B, then the same should be true in that other preference profile. And if it is not the case, then so B is preferred over A, then this should also be the same in the society ranking. So all these candidates, B, C, D, whatsoever, they shouldn't play any role. This is what we call independence of irrelevant alternatives. And now the point is the following. If a ranking rule does not fulfill IIA, it is strategically vulnerable. So what this means is that for a routing rule not to be strategically vulnerable, it is necessary that this ranking rule also fulfills this independence of irrelevant alternatives. And then to show that every reasonable voting rule is strategically vulnerable, all that you have to do is you have to show that it cannot be independent of irrelevant alternatives. We won't have time to go through all the details of the proof, but let's at least talk about how one shows that this lemma, meaning that if independence of irrelevant alternatives is not fulfilled, that then this voting rule, this ranking rule is strategically vulnerable. So if the ranking rule does not fulfill independence of irrelevant alternatives, this means that there have to be these two preference profiles. Such that one candidate, every agent prefers A over B or the agents that prefer A over B are the same in the first and in the second preference profile. But we'll have that in one case A will be preferred over B in the final ranking of society, and in the other B will be preferred over A. And what you now do is we consider the sequence of ranking profiles which start with the profile without the prime and then they continue with the prime. And now what has to happen? So what we have now is a sequence of preference profiles of this form. And what will happen now is we'll start with t being equal to n, in which case we have this preference profile, and so A will be preferred over B in the society ranking. And then reduce n one by one. And eventually we will arrive at this profile, and then suddenly B is preferred over A. But what does this mean? This means at some point in between there has to be a switch between whether A wins against B or B wins against A. And the interesting thing is that this only depends on a single agent's report, because we are changing just one agent's preference at a time. And in between there has to be the switch somewhere, because this cannot be continuous, because we'll always have to say that one of the two will have to win against the other. And this is exactly the agent that can then misreport. So there has to be an I such that A is ranked before B on the one where agent I is reporting the preference profile without the prime, and B is ranked before I if we change almost nothing except for the report of agent I. And now, if this agent actually prefers B over A, then agent I can misreport the one with a prime instead of the one without the prime. Or we might also have just the opposite. But then, and these are the things that we've seen so many times, that then we just do, they can just do misreport the opposite way. This is the kind of argument that we've actually seen before, because the mechanism doesn't actually know whether B should be B is preferred over A, or A is preferred over B. And if now the mechanism incentivizes truthful reporting, then this has to work both ways, so that if my true preferences are these, then I shouldn't report the others, and also vice versa. Good. So the point that you should keep in mind here is exactly this, that there has to be some lack of continuity, and some agents has to decide this at some point. And this is why this agent then does have some control over the outcome. And now we can move forward to actually stating the impossibility theorem. To this, let's introduce one further definition. We say that a ranking rule is unanimous if the following condition holds, namely that if candidate A is preferred to B by every agent I, if candidate A is preferred to agent B for all agents I, then candidate A will be ranked better in the ranking than B. This feels like a very, very natural property for a ranking rule, that actually everybody agrees that A is better than B, then why on earth should A not be ranked higher than B in the society ranking? But the annoying thing is that all of this together that we're asking now, all of this which feels so natural, doesn't work together. And this is the following theorem. This is called Arrow's theorem. Which says that a ranking rule for 3 or more candidates fulfills unanimity and independence of irrelevant alternative only if it is a dictatorship. So a dictatorship, that's just a ranking rule which just takes one agent's ranking and uses it as the society ranking. And now what this theorem is telling us is that, okay, this property, this felt so clearly natural, but then combining this with the independence of irrelevant alternative, which doesn't feel quite as natural, but is necessary for a ranking rule not to be strategically vulnerable, Well, all we end up then with is actually a dictatorship. Unfortunately, we won't have time to go through the proof of this, but it's not extremely complicated. You've already seen with the argument between strategic vulnerability and independence of irrelevant alternatives that how these arguments will work. Because what then happens is that you just compare many different preference profiles. You see that then one agent gets constantly, one candidate is constantly ranked at the top or constantly ranked at the bottom. And then you again go through this and see that one agent will actually make the difference whether this candidate will be ranked at the top or at the bottom. And this then eventually also means, because of the independence of irrelevant alternatives, that this agent can also influence the rest. Because this agent then can decide not to rank this candidate at the very bottom or very top, but anywhere in between. And this is then due to the independence of irrelevant alternatives. Suddenly this agent can determine everything. This only works if you have 3 or more candidates. If you have only 2 candidates, then of course all of this is not true. Because what would you do then? Well, then there are only 2 rankings. And what you could do, for example, is just do a majority vote. Which of the 2 is actually more preferred? So the crucial point is that the combination of this independence of irrelevant alternatives together with 3 candidates, that this will actually be problematic. In the lecture notes, you'll find more details about how this proof works. And there's also an analogous theorem for voting, which is the Gilbert-Satterthwaite theorem, which more or less states the same. It is a little more difficult. It then relies on Arrow's theorem to prove it, but eventually, I guess, at least I wasn't surprised to see this, because once you see that you cannot do ranking, how should you be able to do voting? Because voting is so much related, and if you had a way to do this voting without strategic vulnerabilities, then you could also translate this into a ranking rule. So it's a little unfortunate that we have to end our lecture on voting with these very negative news. But this still doesn't mean that there's no point in thinking about smarter voting rules. Namely, the one thing that you should definitely be asking is who should win the election? What is a good way to determine the society ranking or the winner of a presidency? And also, maybe you can somehow design ranking rules or voting rules which are less strategically vulnerable than others. And indeed, that has been done. So if you then only have preferences of the form of a form which are maybe expressed in terms of a political spectrum somewhere between left and right, and somehow this is a possible way to express all the preferences, which means you wouldn't have like cyclic preferences that somebody prefers A over B over C, somebody else prefers B over C over A, and then somebody prefers C over A over B. Then indeed there are non-trivial strategic voting rules if you have this kind of a structure. Overall, I think this is still a very important topic to think about, and I hope that you now have at least an understanding of what principles to keep in mind when to design voting or ranking rules, and maybe also you've now at least to somehow adjusted your expectations that you cannot hope to get everything with your voting rules. This is it for today. I hope you enjoyed this. Please do let me know if you have any questions. See you next time. Stay safe. Bye.